Is Earth actually a top-tier planet, or just good enough? From school, movies, and even a lot of science videos, you get one big assumption pushed into your brain. Earth is the reference point for life, the Goldilocks world, the standard everyone else gets compared to. But in 2014, two astronomers, René Heller and John Armstrong, proposed something uncomfortable. There could be planets that are objectively better for life than Earth. They called them superhabitable worlds. So you haven't just grown up on a random rock, you may have grown up with the wrong default idea of what ideal for life means. Superhabitable doesn't mean magical or sci-fi, it just means that when you plug the numbers into physics and climate models, some kinds of planets come out looking more stable, more productive, and more long-lived for life than our own. Start with the basic recipe. If you ask the models, what size planet looks best for long-term habitability, the answer is not exactly Earth. The sweet spot tends to be a bit bigger, around 1 to 2 times Earth's mass, and about 1.2 to 1.3 times Earth's radius. Earth's radius is about 6,370 kilometers, or about 3,950 miles. A superhabitable candidate might be closer to 7,600 to 8,300 kilometers, roughly 4,700 to 5,100 miles. What would that feel like for you standing on the surface? Gravity would likely be higher, maybe 1.2 to 1.4 g instead of 1 g. If you weigh 70 kilos on Earth, about 154 pounds, your body on that world might feel like 80 to 98 kilos, around 175 to 215 pounds. It would feel like you are always carrying a small backpack, but your bones, muscles, and heart would have evolved for that from the beginning. Why is this extra gravity such a big deal for habitability? Because more mass and slightly stronger gravity help the planet hold on to a thicker atmosphere and maintain geological activity for longer. A thicker atmosphere means better shielding from radiation, more stable temperatures, and more room for gases like carbon dioxide and water vapor to cycle without everything freezing or boiling away. A geologically active interior, with volcanism and plate tectonics, keeps recycling carbon and nutrients between the crust, the oceans, and the air. For life, that is long-term climate control. But a planet is only half the story. The other half is the star. Here is the next harsh question. Is our Sun even the best type of star to live around? Your Sun is a G-type star, a yellow dwarf with a total lifetime of around 10 billion years. We are already about 4.5 billion years in. That means Earth probably has only a few billion years left before the Sun gets bright enough to push our climate into a dangerous, hot regime for complex life. Heller and Armstrong argued that if you care about how long life can keep going, you should look at slightly smaller, cooler stars called K-dwarfs, the orange stars. K-dwarfs burn their fuel more slowly. Their lifetimes can be 20, 30, even up to 70 billion years, several times longer than the Sun's. From a biological point of view, that is extra time on the clock. If life starts early on a planet around a K-dwarf, it does not get rushed toward the end of the habitable window as quickly as we do here. So how does this play with the habitable zone, the distance band around a star where liquid water can exist on a planet's surface? Around a cooler star, the habitable zone sits closer in and is physically narrower, but the key factor is stability over time. Because K-dwarfs brighten more slowly as they age, their habitable zones drift outward more slowly. That means a planet in the right orbit can stay in the liquid water zone for tens of billions of years, not just a few. On Earth, life has had roughly 4 billion years to develop, from microbes to you. On a superhabitable world around a long-lived orange star, the window for life could be twice as long or more. That is extra time for ecosystems to recover from disasters, for complexity to grow, and for intelligence, if it appears, to spread and stabilize. There is another key detail. A thicker atmosphere on a slightly larger planet around a calmer star could smooth out climate swings. You get fewer deep freezes, fewer total boil-offs, less violent radiation from the star. The planet does not have to be perfect, it just has to give life fewer game-over moments. Now comes the part that really hits your ego. What happens when you start adding up all these factors across the whole galaxy? Take billions of stars, then ask, how many have long, calm lifetimes like K-dwarfs? How many have rocky planets a bit bigger than Earth in the right orbit, with the right mass range, where gravity and atmosphere look like they could hit that superhabitable sweet spot? When people run those statistics with our current exoplanet data, Earth starts to look less like the pinnacle and more like one point in a much bigger distribution. If superhabitable worlds exist in large numbers, there may simply be more of them than true Earth clones. In straightforward terms, that means if you could randomly pick a life-bearing planet somewhere in the Milky Way, the average one might not look like Earth at all. It might be a bit larger, a bit heavier, wrapped in slightly thicker air, circling a quieter orange star with a longer, more forgiving life window. From that perspective, Earth is not the gold standard. It is closer to a baseline model that proves life can work. A civilization on a superhabitable planet, looking at us with their own telescopes, might see a world around a hotter, shorter-lived star and say, interesting, but risky, shorter lifetime, tighter margins. So now you're stuck with a tougher question. If Earth might only be a mid-tier world, how do scientists actually score planets and decide which ones look more promising for life than the one you're standing on? So how do you actually rate a planet when all you can see is a tiny dip in starlight and a few numbers on a screen? Astronomers don't just look at Earth-sized and call it a day. They now use different habitability indices, basically scorecards, that roll a bunch of things together. How much energy the planet gets from its star, the planet's size, its mass, its estimated surface temperature, sometimes even how stable its orbit is. Out of that you get a number, a habitability score. Here's the uncomfortable part. Some planets we've found already score higher than Earth on these scales. That does not mean we know they're better. We don't have maps, we don't have pictures, we usually don't even know the atmosphere yet. It just means if you feed the physics into the model, the parameters say, this one could be even more comfortable for life than Earth, if everything else lines up. So the obvious question is, what knobs on that scorecard matter the most? One of the biggest is radius and mass. Not just is it big, but is it in the right size range to stay rocky, keep its air and not turn into a gas ball? Mars is a good warning sign. Its radius is about 0.53 Earth radii, a bit over 3,300 kilometers, about 2,100 miles. That's small. Small planets cool fast. Their cores shut down, their magnetic fields die, and their atmospheres leak into space over billions of years. Mars lost most of its thick early atmosphere and a lot of its water because it just doesn't have enough gravity and internal heat to hang on to them. Go too big, and you hit the opposite problem. Above roughly 1.5 to 2 Earth radii, a lot of planets stop being supersized Earths and start behaving more like mini Neptunes, thick layers of hydrogen and helium, high-pressure ices, deep gas envelopes. You don't get a clear rocky surface you can walk on, you get crushing atmospheres and high-pressure chemistry. The superhabitable models like the middle ground, roughly 1.2 to 1.3 Earth radii, and up to about 2 Earth masses. In that range, the planet is almost certainly still rocky, but with stronger gravity and better air retention. Think of a world a bit larger than Earth, with 1.2 or 1.3 G at the surface, strong enough to keep a deep atmosphere, but not so intense that you sink into gas layers. That size range is where the models say, okay, this is physically promising, but size alone doesn't tell you if a planet is comfortable to live on. You also need to know how hot or cold it is. That's where equilibrium temperature comes in. Equilibrium temperature is the temperature a planet would settle at if it were just a dark ball absorbing starlight and re-radiating heat. No atmosphere, no greenhouse effect, just pure energy in, energy out. For potentially habitable planets, astronomers usually look for equilibrium temperatures between about 240 and 310 Kelvin. In normal terms, that's roughly minus 33 to plus 37 degrees Celsius, or about minus 27 to 99 degrees Fahrenheit. That sounds like a wide range, but remember, this is before you add greenhouse warming from things like carbon dioxide and water vapour. Take Kepler 442b as an example. Its equilibrium temperature is around 233 Kelvin, roughly -40 Celsius, -40 Fahrenheit. On paper, that looks cold, like a planetary deep freeze. But give it a thicker atmosphere, let greenhouse gases trap more heat, and the real surface temperature could climb into the liquid water zone quite comfortably. So on the scorecard, you're not looking for a planet that is perfectly Earth temperature by default. You're looking for a world that sits in that comfortable fridge range, not a frozen icebox, not a baked oven, and has the right size and mass so an atmosphere can dial the final temperature into the sweet spot. Now, you might ask, if we want thicker atmospheres, isn't there a point where that becomes a problem for creatures like us who need to stand and walk and breathe? This is where the balance between atmosphere depth and you can actually walk there shows up. If you double Earth's surface gravity, you're up near 2G. A 70-kilogram person, 154 pounds, would feel like 140 kilos, over 300 pounds. Even at 1.5G, you effectively add the weight of a full hiking backpack to your body at all times. Climbing stairs is training. Standing still is harder work. For humans, that's rough. For life that's evolved there, that's just normal. The advantage is that stronger gravity can support a denser atmosphere, maybe 1.5 to 2 times Earth's surface pressure or more, and hold on to it for longer. A deeper air column blocks more ultraviolet light, more cosmic rays, and smooths out temperature swings between day and night, and between seasons. High-energy particles get absorbed higher up, turned into heat and harmless light long before they reach the surface. So yes, on a superhabitable world you would feel heavier, your lungs would be pushing against slightly denser air, but in exchange the planet gives life better shielding and more climate stability. The models say there's a sweet zone where gravity is strong enough to do that, but not so extreme that you crush everything flat at the surface. That zone lines up pretty well with that 1 to 2 Earth mass range. Planet size, atmosphere and temperature give you the environment. But for long-term billion-year habitability, there is another factor that shows up again and again: plate tectonics. Plate tectonics is not just about earthquakes and volcanoes, it is your planet's long-term life support system. On Earth, tectonic plates move, dive back into the mantle, push up new crust, and in the process, recycle carbon and nutrients between the rocks, the oceans, and the atmosphere. Carbon dioxide gets locked in rocks, then released again through volcanism. That helps keep the climate in a range where water stays liquid. If a planet is too small like Mars, its interior cools, plate tectonics either never starts or dies quickly, the core solidifies, the magnetic field fades, volcanism slows or stops, and carbon cycling stalls. You can end up with a frozen world or a thin, fragile atmosphere that can't easily recover from big changes. Models suggest that plate tectonics may actually work best on planets up to about twice Earth's mass. In that regime, you have more internal heat, more stress on the crust, and more potential for plates to break, slide, and subduct. That is exactly the mass range superhabitable candidates tend to sit in. So you get a planet that is more massive than Earth, with vigorous tectonics, constantly renewing continents, building mountain ranges, creating fresh coastlines, and steadily cycling carbon. That kind of world is less likely to hit a climate dead end, where the atmosphere locks into an extreme state and can't get out. It's not immune to disasters, but it has more tools to recover from them. So when astronomers look at a distant planet and say, this one might actually score above Earth, they're not guessing randomly. They're piecing together a story from a few key numbers: the star's brightness, the planet's orbit, its radius, its mass, its equilibrium temperature, and what that implies for gravity, air, and tectonics. And some of those stories on paper look better than ours. Which raises the next uncomfortable question. If our star is only okay, and our planet is only mid-range on this scorecard, how does the Sun itself stack up against the stars that might host the truly elite, superhabitable worlds? So how good is your star really, when you compare it to the rest of the galaxy? The Sun feels stable and permanent in your daily life. but on galactic timescales it is only middle of the road. It is a G-type star, a yellow dwarf with a total lifetime of around 10 billion years. Right now, you are roughly halfway through that, about 4.5 to 5 billion years in. That sounds huge, but for biology, that clock is already running down. Now compare that to K-dwarf stars, the orange ones. They're a bit smaller than the Sun, a bit cooler, and they burn their fuel more slowly. Their total lifetimes are not 10 billion years. They can go 20, 30, even up to 70 billion years, depending on their exact mass. That is 2 to 7 times more time than the Sun gives you. If you think in terms of evolution, that matters a lot. Complex multicellular life on Earth has only existed for about the last 600 million years, less than 10% of Earth's age. Technological civilization, your entire recorded history, is only a tiny fraction of that. On a planet around a K-dwarf, the time available for life to start, adapt, recover from disasters, and reach intelligence could be much longer. You are basically living around a star with an early closing time, while other stars keep the lights on far later. Star type is not just about lifetime though, it is also about how violent the star is, especially when it is young. All young stars are more active, they rotate faster, they flare more, and they pump out more high-energy radiation. X-rays and ultraviolet light from those early tantrums can strip atmospheres and hammer the surface of young planets. M-dwarf stars, the small red ones, are especially bad for this. They are very common and extremely long-lived, but many of them throw powerful flares and outbursts even late into their lives. If you put a planet close enough to stay warm around an M-dwarf, you also place it right in the line of fire. K-dwarfs sit in a more favourable zone. They are long-lived like M-dwarfs, but generally quieter, especially once they reach middle age. They still flare, but not with the same constant extreme behaviour you see in many small red stars. That means less atmospheric stripping, fewer sterilising radiation blasts, and a more stable environment for life to persist near the surface. So you get a double benefit, more time overall, and a calmer radiation environment during the crucial billions of years when life is trying to get going and diversify. The Sun, in comparison, is fine, but it's not special. It gives enough stability for life to exist here, obviously, but it does not maximise the time or minimise the risk. There is another slow effect that really matters for habitability, how the star's brightness changes over time, and how that drags the habitable zone around with it. Stars like the Sun do not stay at one brightness forever. As they age on the main sequence, they slowly brighten. That means the habitable zone, the distance where liquid water can exist on a planet's surface, gradually moves outward. A planet that starts in the comfortable band can end up more and more overheated as the star ramps up its output. Earth is already dealing with this long, slow shift. In about 1 to 2 billion years, current models suggest that the Sun's increased brightness will push Earth toward much higher temperatures. Oceans will evaporate more quickly, the greenhouse effect will intensify, and complex life, things like large plants and animals, may find it very hard to survive long before the planet becomes physically uninhabitable for any life at all. Around K-dwarfs, this drift is slower. Because these stars evolve more gently, their habitable zones move outward more slowly over tens of billions of years. A planet parked at the right distance can stay in the life-friendly band for far longer than Earth can. The climate still changes, nothing is completely frozen in time, but the rate of change is slower and the margin for life to adapt is larger. This is one of the reasons Heller and Armstrong and other researchers after them pointed straight at K-dwarfs when they talked about superhabitable worlds. When they formalised the idea, one conclusion stood out very clearly. If you want to search for planets that are not just habitable, but especially favourable to life over very long timescales, target K-dwarfs first. They give you the longest stable windows. They are common in the galaxy. They flare less violently than many M-dwarfs. Their habitable zones move slowly enough that a planet in the right orbit can enjoy tens of billions of years of relatively mild conditions. For biology, that is an enormous advantage. It means more time for ecosystems, more time for biodiversity, more time for evolution to explore possibilities that Earth will simply never have the years to reach. So line up your options. On one side you have a G-type star like the Sun, about 10 billion years total, halfway through, with a habitable window for complex life that might have only a couple of billion years left before conditions get too hot. On the other side you have a typical K-dwarf, maybe 30 billion years of total lifetime, with a slow, steady energy output and a habitable zone that moves outward gently. If life arises easily wherever conditions are right, then the statistics are harsh. The average biosphere in the Milky Way is not sitting on a planet around a sun twin. It is more likely sitting around a quieter orange star, with far more time in the bank than Earth will ever get. Those planets get more rolls of the dice for life to start, for complexity to appear, for intelligence to stabilize. That leads to another difficult question. If many of the best planets around these long-lived stars are also a bit more massive than Earth, with higher gravity and thicker atmospheres, does that create a strange trade-off where life gets easier, but leaving the planet gets much harder, maybe nearly impossible with normal rockets? So what happens when you push that slightly bigger than Earth idea further, and you end up on a world where gravity is not just a bit stronger, but dominates everything your civilization can do? Astronomers use the term super-Earth for rocky planets that are more massive than Earth, but still much smaller than Neptune. In numbers, that usually means something like 1 to 10 times Earth's mass. They are not gas giants, they are not mini Jupiters, they are mostly rock and metal with maybe some deep oceans and thick atmospheres. When people talk about superhabitable planets though, they almost never mean the whole 1 to 10 range. The promising ones cluster at the low end, around 1 to 2 Earth masses, and roughly 1.2 to 1.5 Earth radii. From the surface, that extra mass translates directly into higher gravity. At 1.5 to 2 times Earth's mass, you might feel something like 1.3 to 1.7 g depending on the radius. If you weigh 70 kilos on Earth, about 154 pounds, your body would feel like 90 to 120 kilos, 200 to 260 pounds on that surface. Standing up is harder, running is slower, but your bones and muscles, if you evolved there, are built for it. It's demanding but not impossible. That extra gravity gives the planet a big advantage that Earth never had. It holds onto gas much more efficiently. A 2-Earth mass super-Earth can sustain a denser atmosphere without watching it slowly leak into space. Light molecules like water vapor and even some hydrogen are less likely to escape. That lets the climate system run with more pressure to work with and more greenhouse gases without losing everything over a few billion years. A denser atmosphere is like turning up the padding between space and the ground. Ultraviolet light, X-rays and charged particles from the star have to fight through more air before they reach the surface. On Earth, the ozone layer and the bulk of the atmosphere already cut down a lot of that. On a super-Earth, that shield can be thicker by default. For life, that means fewer mutations from random high-energy hits, more stable conditions at sea level, and an easier time keeping liquid water where it counts. Water is where the super-Earth advantage becomes really obvious. Look at Mars. It started with water and a thicker atmosphere, but its low gravity and dead core meant it could not hold those long term. Much of its atmosphere was stripped away, and with it a lot of its surface water. Today you see dry riverbeds and minerals that formed in liquid water, but the oceans are gone from the surface. Now scale up instead of down. Take a rocky world with around 1.5 times Earth's radius, maybe about 9,500 kilometers, nearly 6,000 miles across. Give it strong gravity, a working magnetic field, and a deep global ocean. Because gravity is higher and the atmosphere is thicker, water molecules have a much harder time escaping to space. The ocean basins can stay filled for billions of extra years. You can have Pacific-sized oceans that are not just wide, but thousands of meters deeper than Earth's, and they do not slowly bleed off into space the way Mars did. From a purely biological point of view, that is close to a dream setup: stable oceans, strong shielding, plenty of time. So where is the catch? The catch shows up the moment an intelligent species tries to leave. To get off any planet, you need to reach escape velocity, the speed where your rocket no longer falls back and instead climbs out of the gravity well. For Earth, that speed is about 11.2 kilometers per second, roughly 25,000 miles per hour. That already forces huge rockets. The Saturn V that sent Apollo to the moon stood about 110 meters tall, around 360 feet, and most of it was fuel. On a 2-Earth mass super-Earth with a radius maybe 1.3 times Earth's, the surface gravity is higher and the escape speed climbs to something like 1.4 to 1.5 times Earth's. Now you're talking 15 to 17 kilometers per second, over 30,000 miles per hour, just to get free. With normal chemical fuel, the kind you burn in rockets today, the math gets brutal very fast. One study showed that a chemical rocket reaching orbit from a world like that would have to be many times more massive than Saturn V. Maybe a skyscraper of propellant, just to lift a tiny payload to space. At that point, classic rocketry stops being a practical option. The planet is not just heavier, it is a gravity prison. You can build planes, you can build towers, you can build satellites if you somehow get them up there with exotic methods, but pure chemical rockets struggle to cross the line from atmosphere to orbit. You need something like space elevators, extreme nuclear rockets, or physics we do not yet use in real engineering. So you get a strange, almost unfair trade-off. Life on a super-Earth can thrive. Gravity makes air retention easier, oceans longer-lived, and radiation shielding stronger. Evolution gets a deep, stable playground, full of forests, oceans, and giant animals adapted to high gravity and thick air. But an intelligent species there might be stuck staring at their sky for millions of years, with no realistic way to build a rocket big enough to leave. From your point of view, that world looks like paradise on the ground and a nightmare for a space program. And that raises another question that cuts even deeper. If the most biologically rich planets in the galaxy are the ones that are hardest to launch from, what does that do to their land, their water, and their climate over billions of years when you tune the geography itself for maximum habitability? Why does Earth's map look normal to you when it might actually be a bad layout for life compared to what physics allows? Look at a globe, you see big bulky continents and deep wide oceans. It feels natural, but climate models say this setup is just okay, not amazing. If you wanted to design a planet to maximize life, you probably would not copy Earth's land-sea pattern. You'd break the continents apart more, you'd keep more of the ocean shallow, and you'd push the geography toward lots of edges, lots of transitions, lots of overlap between land and water. On Earth, you've got a few big land blocks, like Eurasia, Africa, the Americas, separated by huge deep basins like the Pacific, which averages around 4,000 meters deep over 13,000 feet. That layout leaves massive dry interiors, like Central Asia or Central Australia, and huge stretches of low productivity open ocean. It works well enough to support complex life, but it's nowhere near the maximum biodiversity you could squeeze out of the same sunlight. So what does a better layout look like? One of the biggest levers is coastlines. On Earth, coastal regions, the zones where land meets ocean, are some of the most biologically productive areas we have. Estuaries, mangroves, shallow continental shelves, coral reefs, deltas, these are the places where nutrients from land wash into the sea, where sunlight can hit shallow water, where you get intense food chains. On a superhabitable world, you'd aim for more of that. Climate and habitability studies suggest a really good setup might be around 30 to 50% of the surface covered in land, but not in a few giant continents. Instead, you get lots of medium and small continents, plus chains of large islands. Think global archipelago, a planet where almost every patch of ocean is within a few hundred kilometers or a few hundred miles of land. That kind of layout multiplies coastlines. More edges mean more mixing zones, more habitats, more places where land plants, shallow water ecosystems, and nutrient cycles lock together. From orbit, that world might look like scattered green and brown shards embedded in blue, with almost no vast, empty mid-ocean deserts. But land shapes are only half of it. You also want to tune how deep the oceans are. Here's the key question: are Earth's oceans too deep for maximum life? Deep ocean is not bad, but it's relatively low in productivity per square metre. Sunlight in clear water only penetrates down tens of metres, maybe 100 metres at most, 300 feet or so. Below that, photosynthesis shuts down and you're in dark, low-energy territory. The bulk of the biomass sits near the surface or on shallow shelves. On a superhabitable planet, you'd probably want a larger fraction of the ocean sitting on broad continental shelves in water, maybe 10 to a few hundred metres deep, 30 to a few hundred feet. In those depths, sunlight can reach most of the water column, mixing can bring nutrients up from the seafloor, and photosynthetic life can use much more of the available stellar energy. So imagine the same amount of light hitting the top of the atmosphere as Earth gets, roughly 1360 watts per square metre at the top. But the planet's geography is arranged so that a larger share of that energy hits shallow productive seas instead of deep dark basins. You end up with more total biomass, more food, more complexity from the same star. It's not magic, it's just geometry and ocean depth doing you a favour. Now think about stability. Earth's continents haven't always been in their current positions. In the past, they've smashed together into supercontinents like Pangaea. Those supercontinents are linked to extreme climates, huge dry interiors far from the ocean, brutal temperature swings between seasons, and strong vulnerability to long-term climate shifts. With one giant landmass, if the climate system shifts the wrong way, huge areas can become desert or ice-covered. So ask yourself this: what happens to evolution when your planet regularly builds giant supercontinents, then tears them apart again? Each time you're pushing ecosystems through extreme cycles. You can get intense bursts of diversification along new coastlines and mountain ranges, but you also get long periods where large parts of the planet are harsh, unstable, and vulnerable to big die-offs. Mass extinctions in Earth's history are tied to things like volcanic outpourings, climate swings, and possibly impacts, but continent layout feeds into how hard those hits land. A superhabitable planet with more fragmented continents would dampen a lot of that. Many smaller land masses, all close to the moderating influence of the ocean, means fewer huge dry interiors and fewer regions that swing between climate extremes. Oceanic air can move over more of the land, smoothing out temperatures and precipitation. That doesn't stop all disasters, but it gives life a more steady background to work on. Evolution gets to grind forward more continuously instead of constantly rebuilding after big crashes. Then there's the balance between deserts and wet tropics. Look at Earth right now. Big deserts like the Sahara, the Arabian Peninsula, Central Australia, parts of Western North America and Central Asia. These are places with low rainfall, high evaporation, and limited productivity. They cover a significant fraction of the land surface. On a superhabitable world, climate models suggest you'd aim for wider tropical and temperate belts that stay wet, or at least moderately moist over huge distances. Warmer average temperatures, more evaporation from the oceans, and lots of coastlines feeding moisture inland can extend forest and grassland zones much farther from the equator than on Earth. Instead of a single Amazon basin stretching a few thousand kilometers, a superhabitable planet might have Amazon-level regions looping around large parts of the world, tens of thousands of kilometers, or tens of thousands of miles, of warm, wet, high-productivity land. Deserts would still exist. You always have some regions in the rain shadows of mountains or under special wind patterns, but they would be smaller slices of the total, not major blocks. For life, that means more stable, high-productivity zones, fewer huge dead patches where only sparse, slow-growing organisms can survive, and less sensitivity to small climate wobbles. If rainfall shifts a bit in one region, other wet regions pick up the slack. The biosphere as a whole stays thick and resilient. So, stack this up. A superhabitable world has slightly higher gravity to hold thicker air, long-lived oceans under a calmer star, and a land-sea layout tuned for maximum coastline and shallow water area. Earth, compared to that, is functional but inefficient. Big empty oceans, big dry interiors, supercontinents in its past, and large deserts all eat into the total amount of life it can support and the stability of that life over time. And that raises the next point. If you give a planet better geography, better oceans, and a calmer star, what happens to the overall power of its biosphere? How much more alive can a world like that be compared to Earth, when you crank up productivity and push the whole system into overdrive? How alive can a planet actually be compared to Earth? And what does it feel like to stand on one that's running hotter, faster, and harder than anything you've ever seen here? On Earth, life captures on the order of 100 to 130 petawatts of solar energy through photosynthesis. That's a huge number, but it's limited by geography and climate. Large deserts, deep, low productivity oceans, ice caps, and harsh interiors cut down how much of the sun's power actually gets converted into living tissue. A big chunk of the planet's surface is basically running at low output. On a superhabitable world, a lot of those bottlenecks get removed. More of the surface sits in mild, wet, well-lit climate zones. There are more shallow seas instead of deep, dark basins. There are more coasts, more rain-fed regions, and fewer giant deserts. That means a larger fraction of incoming stellar energy get routed into actual biology instead of bouncing off sand, snow, or empty water. The total net primary productivity, that how alive is this planet number, could be far above Earth's, just because the layout, the star, and the atmosphere are tuned better. So the next question is, does that kind of world have to be dangerously hot, or just a bit warmer in a controlled way? Models for superhabitable planets usually put them slightly warmer than modern Earth, not boiling, but shifted upwards by about 5 to 10 degrees Celsius on average, so roughly 9 to 18 degrees Fahrenheit. If Earth's global mean temperature is around 15 degrees Celsius, a superhabitable world might sit at 20 to 25 degrees Celsius, 68 to 77 Fahrenheit, as its normal. That bump in temperature pushes more of the planet into the zone where water is liquid year-round, rain is frequent, and plants can grow continuously. Cold high-latitude regions shrink, permafrost belts get thinner or disappear. You end up with larger areas that behave like today's temperate forests, tropical forests, and warm oceans. In simple terms, more of the map is green and busy, less of it is frozen or baked, but warmth alone is not enough. You also need the air to help, not fight you. On a superhabitable world, the atmosphere is likely thicker than Earth's. Surface pressure might be 1.5 to 2 bar instead of 1 bar. That's like compressing more air into the same space. If the oxygen fraction is also higher than Earth's 21%, say 25 to 30% or more, the effect on metabolism is huge. Earth has already tested this. During the Carboniferous period about 300 million years ago, oxygen levels rose significantly above today's value. Insects and other animals responded by growing larger because oxygen could diffuse into their bodies more efficiently. You had dragonflies with wingspans over 70 centimeters, more than 2 feet. On a superhabitable planet with constant high productivity, that high oxygen, high metabolism state might not be a short-lived spike. It could be the default. Forests, oceans, and microbial mats would be pumping out oxygen and cycling nutrients at high speed all the time. Animals could afford faster metabolisms, more active lifestyles, and possibly larger sizes, as long as gravity doesn't push too hard in the opposite direction. Of course, more warmth and more water vapor also mean more storms. So does this just turn the planet into a permanent disaster zone? Not necessarily. With more water vapor in the air, you do get frequent storms, but if the planet's rotation rate, axial tilt, and continent layout are in the right ranges, those storms can settle into regular, predictable patterns. Instead of rare, ultra-violent hurricanes like you see on Earth, you might get more frequent but moderate systems that move heat and nutrients around without tearing everything apart each season. Think in terms of strong but routine weather, regular rain bands, reliable storm tracks that feed forests and shallow seas, rather than random record-breaking events that wipe out coastlines. Ocean-buffered climates and broken-up continents help keep temperature gradients under control, so the atmosphere has less incentive to spin up extreme megastorms. The system spends more time in delivery mode and less in catastrophe mode. So what would it actually feel like at ground level for you walking through that kind of biosphere? At 1.2 or 1.3 G, your body feels heavier than on Earth. A 70 kilogram person, 154 pounds, would feel like 84 to 91 kilograms, 185 to 200 pounds. The air at maybe 1.5 to 2 bar would feel denser and richer when you breathe. If you have ever trained at high altitude and then come down to sea level, you know that sense of easy air. Here, that effect is turned up permanently. The sky might look slightly hazier than on Earth because of higher water vapour and thicker air, with the stars' light scattered into a softer glow. Temperatures in many regions would sit in the low to mid-20s Celsius as a normal baseline, high 70s in Fahrenheit, warm but not extreme. Forests could be incredibly dense, with multiple layers of vegetation stacking above each other because the light and nutrients support it. Tree analogues might reach tens of meters high, maybe 50 meters or more, over 160 feet, with undergrowth that never really shuts down for winter in many zones. Sound would travel differently too. Denser air carries sound more efficiently, so forests might feel acoustically closer, with animal calls and leaf movement reaching you from farther away. The combination of higher oxygen, warm temperatures, and steady humidity would hit your lungs and skin immediately. For a human body adapted to Earth, it would be intense, maybe overwhelming. For native life, it's normal. And all of this is running on more energy than Earth's biosphere ever sees, because the planet's layout, star and air are built to turn starlight into chemistry with minimal waste. Earth, next to that, starts to look like it's running in a lower gear, with big parts of its surface idling. That leads straight into the next question. Does any real world we've already found actually resemble this biosphere on overdrive template, even on paper? Or is this still purely theoretical? One candidate keeps showing up in the discussions, a planet called Kepler 442b, which, on the numbers, might be closer to the superhabitable recipe than Earth is. Kepler 442b is one of the first real planets where you can say, with a straight face, that on paper it might be a better home for life than Earth, and that is not comfortable to think about. Here are the basics. Kepler 442b. Tube orbits a K-type star, an orange dwarf, in the constellation Lyra, about 1,200 light-years away. It was found by the Kepler Space Telescope through transits, tiny dips in starlight when the planet passes in front of its star. From the depth and timing of those dips, astronomers can estimate its size and orbit. The result is a planet with a radius about 1.34 times Earth's radius. In kilometres, that is roughly 8,500 kilometres across, compared to Earth's 6,370. In miles, that is about 5,300 miles versus Earth's 3,950. Mass estimates, based on typical densities for planets in this size range, put Kepler 4b around 2 to 3 times Earth's mass. That probably means surface gravity in the ballpark of 1.3 to 1.7 g, depending on the exact composition. If you weigh 70 kilos on Earth, about 154 pounds, your body might feel like around 90 to 120 kilos there, 200 to 260 pounds. For you, that is heavy. For life that evolved under those conditions, that is just the default. Critically, Kepler 442b orbits right in the habitable zone of its star. The star is cooler and dimmer than the Sun, so the planet orbits closer in, but not so close that it gets baked. Its orbital period is around 112 days. That means a year there is a bit under 4 Earth months long. From the transit data and stellar models, you can estimate its equilibrium temperature, the no atmosphere just absorbing and re-radiating baseline. That comes out to about 233 Kelvin, roughly minus 40 degrees Celsius, minus 40 Fahrenheit. That sounds very cold at first glance, colder than almost anywhere on Earth's surface, but this is before you add any greenhouse effect from an atmosphere. Earth's equilibrium temperature without greenhouse warming is also well below the actual average surface temperature. If Kepler 442b has a thicker atmosphere than Earth, with enough greenhouse gases like carbon dioxide and water vapour that -40 baseline can shift up into a range where liquid water is stable on the surface over large areas. So when scientists run Kepler 442b through various habitability indices, the planet scores high. Some of those indices actually give it a higher habitability score than Earth. That does not mean it is truly better. It means its star type, orbit, size, and estimated temperature fit the superhabitable template more closely than Earth's numbers do. It sits around a K-dwarf star, not a G-dwarf like the Sun. It is somewhat bigger and more massive than Earth, which is good for atmospheric retention and tectonics. It orbits in a region where the star's energy output appears compatible with surface liquid water. This is why you will see researchers cautiously use words like superhabitable candidate, or say that Kepler 442b checks many of the boxes for a world that could outperform Earth for life. It is not just random optimism. When you look at the theory, it wants a slightly larger rocky planet around a long-lived K-dwarf in the right part of the habitable zone, with an equilibrium temperature that can be raised into the comfortable range by a moderate greenhouse effect. Kepler 442b matches that outline more closely than your own planet does. But there is a hard stop here. The big unknown is the atmosphere. Right now, we have no direct observation of Kepler 442b's air. We do not know if it has a thick nitrogen-oxygen style atmosphere, a carbon dioxide heavy blanket, a thin Mars-like envelope, or even a mini Neptune-style hydrogen layer that would make the surface uninhabitable. All the nice habitability scores are conditional. They basically say, if this planet has a suitable atmosphere, it could be very good for life. That if is doing almost all the work. The problem is distance and brightness. Kepler 442b is about 1,200 light-years away and orbits a relatively faint star. To read a planet's atmosphere, you usually need to catch starlight passing through the air during transits and then split that light into a spectrum, looking for the fingerprints of gases like water vapour, oxygen, methane, carbon dioxide, and ozone. With today's instruments, especially at that distance and brightness, Kepler 442b is simply too faint for a clean atmospheric spectrum. This is why so much effort is going into building new telescopes. The James Webb Space Telescope is already pushing the limits for closer, brighter systems, mainly around smaller stars. But for planets like Kepler 442b, you need even more targeted tools. Future missions like the proposed Habitable Worlds Observatory are being designed with one main goal: directly image Earth-sized planets around nearby stars and take detailed spectra of their atmospheres. Kepler 442b itself may never be the one we study in detail. It is too far, too faint, and not in our local neighbourhood. But it acts as a template. It tells astronomers what to look for closer to home: planets around K-dwarfs, with radii around 1.2 to 1.4 Earth radii, masses in the 1 to 3 Earth mass range, orbits in the right part of the habitable zone, and equilibrium temperatures in that cold but fixable band. So you end up in a strange situation. You know the numbers for this world well enough to say, if the atmosphere cooperates, this place could be more hospitable to life than Earth. You also know almost nothing about the actual conditions on the ground. It could be a thriving ocean planet with thick clouds and deep biospheres, or a dead frozen rock with the wrong mix of gases, or a mini Neptune with no solid surface to stand on. And that raises the next tension point. If one candidate like Kepler 442b already looks this promising just from the limited data we have, how many other could be better than Earth worlds are already on our lists, half understood, sitting in the catalogues under names like Kepler 452b, Kepler 62f, TRAPPIST 1e, and others. Some planets on our list look almost like upgraded versions of Earth until you check the fine print and see how easily they can slide into too hot, too cold, or blasted by their star. Take Kepler 452b. It's about 1.6 times Earth's radius, so roughly 10,000 kilometers across, around 6,200 miles. It orbits a star that's very similar to the Sun, and that's why people like to call it Earth's cousin, or even older, bigger Earth. On the surface, that sounds like a superhabitable dream. Bigger planet, possibly stronger gravity. sun-like star right in the habitable zone, but its star is older and brighter than the Sun. As stars age, they get more luminous, and that pushes the habitable zone outward. Kepler 452b is probably sitting closer to the inner edge of its star's habitable zone than Earth is to the Sun's. That means it may be getting more energy than is comfortable for long-term oceans and mild climates. If its atmosphere has a strong greenhouse effect, it could be trending toward a super-Venus state, with runaway heating and thick hot air, rather than a lush, mild super-Earth. On a basic habitability checklist, it scores well at first glance, then picks up a warning label, maybe too warm. Now look at the other side of the scale, Kepler 62f, the cold sibling. Kepler 62f is about 1.4 Earth radii, so maybe 8,900 kilometers in radius, around 5,500 miles. It orbits a cooler star and sits out in the outer region of that star's habitable zone. That automatically raises the risk of being too cold. Without a strong greenhouse effect, Kepler 62f could easily be a frozen snowball, global ice, low evaporation, and a sluggish climate. But if it has a thick atmosphere loaded with carbon dioxide and maybe other greenhouse gases, that outer position can be an advantage. The planet could warm up into a stable ocean world with deep global seas and maybe scattered island continents. Same orbit, different atmosphere, completely different outcome, either an ice-locked world or an endless water planet. Right now we do not know which one it is. Then there are the nearby could-be worlds that suffer from a different problem, their stars. Gliese 667cc and Proxima Centauri b both sit in the habitable zones of M-dwarf stars. Very small, very long-lived, very common in the galaxy. On paper that sounds great. Long lifetimes, potentially stable orbits, and plenty of time for life. The issue is that many M-dwarfs are extremely active. They flare hard and often, throwing out intense bursts of X-rays and ultraviolet light, plus streams of charged particles. If a planet has to orbit very close to stay warm, which it usually does around an M-dwarf, it ends up right next to this chaotic behaviour. Over time, those flares can strip atmospheres, erode ozone layers, and directly damage surface life. For Gliese 667cc and Proxima b, that's the big question. Can they keep their air? If they have strong magnetic fields and thick atmospheres, they might be able to shield their surfaces and stay habitable. If their fields are weak or their atmospheres thin, they could be barren, stripped worlds despite being in the right orbital zone by simple energy calculations. Again, promising numbers, serious caveats. TRAPPIST-1e is a different kind of favourite. It's much closer to us, about 40 light-years away, in a compact system of 7 rocky planets around a tiny M-dwarf star. TRAPPIST-1e is very close to Earth's size, with a radius near 1 Earth radius and a mass in the same ballpark. It orbits in a region considered potentially habitable, and because the star is small and dim, the planet orbits close in, making transits frequent and strong enough to study with the James Webb Space Telescope. Recent JWST observations suggest that TRAPPIST-1e does not have a thick, puffy hydrogen atmosphere like a mini Neptune. That is good news. A thick hydrogen envelope would probably make the surface uninhabitable for Earth-like life. Instead, it looks more like it might host a denser secondary atmosphere, something more like Earth's nitrogen-oxygen mix, or Titan's nitrogen-methane style, though we do not have a full chemical breakdown yet. That makes TRAPPIST-1 one of the top targets for future, deeper atmospheric studies. It sits in that narrow band of rocky, right size, right place, and not obviously wrong in the atmosphere department. So you have this set of worlds, Kepler 452b, Kepler 62f, Gliese 667cc, Proxima b, TRAPPIST-1e, and others that keep showing up in lists of potentially habitable or Earth-like exoplanets. Some of them look too hot, some too cold, some sit by angry stars, some look very promising, yet not one of them is officially labelled superhabitable. The reason is simple and frustrating for almost all of them, radius, rough mass, and orbit. You can estimate equilibrium temperature and classify the star. You can say, this one is probably rocky, this one is probably into the habitable zone, this star is stable enough, and you can feed those data into habitability indices, but you almost never know the key details, the real atmosphere, the actual surface conditions, the cloud patterns, the ocean coverage, the land layout. Right now you're in a stage where you can see the silhouettes of these planets, but not their faces. You know their outlines and some bulk properties, but not the fine structure that actually decides whether they are deserts, ocean worlds, Venus-like ovens, frozen, or something close to a true superhabitable Eden. And that leads straight to another layer of the story. Planets are not the only possible homes for supercharged biospheres. If giant planets in the right orbits have big rocky moons, those moons, powered by both starlight and tidal heating, could be their own superhabitable worlds, hiding in plain sight as just satellites. Here's a twist that's easy to miss. Some of the best homes for life might not be planets at all. They might be moons. You're used to thinking of moons as secondary little frozen rocks or aeroless spheres going around the real worlds. In our system, that's mostly true. You get Europa and Enceladus with buried oceans, Titan with a thick atmosphere, Io with crazy volcanism, but none of them are comfortable, walk on the surface, breathe the air places. René Heller and others have pushed a different angle. If you scale some of these ideas up and put them in the right orbit, large moons around giant planets could actually be superhabitable. Think Europa or Titan. But bigger, warmer, orbiting in a star's habitable zone with liquid water, continents, and a breathable atmosphere. The key extra ingredient here is tidal heating. When a moon orbits a massive planet, gravity doesn't just pull once and stop. As the moon moves around, the planet's gravity flexes it, squeezing and stretching the interior. That mechanical flexing converts orbital energy into heat. You see this in our own system on Jupiter's moon Io, which is about 3,640 kilometers across, roughly 2,260 miles. Io is constantly flexed by Jupiter and the other moons, and the result is brutal volcanism, lava lakes, and one of the most geologically active bodies we know. Now scale that idea down a bit. On a superhabitable moon, you don't want Io-level insanity, you want moderation. You keep tidal heating strong enough to power tectonics, volcanism, and subsurface circulation for billions of years, but not so extreme that the surface melts down or becomes a permanent eruption zone. Combine that internal heat with a position in or near the star's habitable zone, and the moon can maintain liquid water, active geology, and a thick atmosphere for a very long time, even if it's slightly farther from the star than a standard habitable planet would be. You get built-in geothermal energy on top of starlight. There's another advantage that's easy to overlook. The giant planet itself can act like a shield. Many gas giants like Jupiter and Saturn have powerful magnetic fields. Those fields carve out magnetospheres, regions around the planet where charged particles from the star are deflected and trapped. If a moon orbits within that magnetosphere, it may get extra protection from stellar wind and cosmic rays, on top of whatever magnetic field and atmosphere the moon itself has. So picture the stack. The star's heliosphere cuts down interstellar radiation, the giant planet's magnetosphere blocks a chunk of the stellar wind, and the moon's own magnetic field and atmosphere take care of what's left. For life sitting on the surface, that's layers of shielding between you and space, which means fewer DNA-destroying hits and more stable conditions over deep time. Light and shadow are more complicated in these systems, but they can help rather than hurt. A moon around a giant planet in the habitable zone moves through a three-body dance: star, planet, and moon. That creates regular cycles of illumination and eclipse. You might get short, frequent eclipses when the moon slips into the giant planet's shadow, plus phases where the planet reflects starlight back onto the moon like a second, dimmer sun. At first, that sounds like it should mess the climate up, constant flickering between light and dark. But under the right orbital conditions, with near circular orbits and stable resonances, those cycles can become highly predictable. The moon's atmosphere and oceans can smooth out the short-term dips in energy during eclipses, Just like Earth's, climate smooths out night and day. Over long timescales, that regular pattern can actually help distribute heat and drive steady winds and ocean currents, instead of wild swings. Put that around a calm K-dwarf star, and you have a system where time shielding and energy input all work together. From the surface, that world would feel very different from Earth. The giant planet would loom huge in the sky, maybe covering a big chunk of the view. You'd see it changing phase from full to crescent over the course of your short orbital month. You'd have regular eclipses where daylight drops, not because of clouds, but because the planet slides in front of the star. Tides in the oceans would be stronger and more complex, driven by both the star and the nearby giant. Those tides help stir coastal zones, move nutrients, and feed coastal ecosystems. The real problem right now is that our detection methods are only just starting to reach this regime. Transit surveys like Kepler and TESS are optimized for spotting planets, not moons. When a planet crosses its star, you see a clear dip in brightness. A moon, especially an Earth-sized one, produces a much smaller signal. It doesn't transit in a simple, repeatable way on its own. Its timing and position change as it orbits the planet. So how do you find one? You look for side effects. A big moon slightly shifts the timing of the planet's transit timing variations, and can tweak the depth or the shape of those dips, transit duration and brightness variations. Astronomers are actively hunting for these patterns. A few candidates have been proposed, but nothing is widely accepted yet as the first clear exomoon detection, especially not an Earth-sized one in a perfect habitable zone. Here's the important bit for the bigger story. The moment we confidently detect a large, rocky, roughly Earth-sized moon in the habitable zone of a star, especially around a K-dwarf or a calm star, the entire conversation about where life is most likely will jump. Because then you're no longer asking only, how many good planets are out there? You're also asking, how many good moons are attached to giant planets in those same zones? And if you add those into the count, the number of potentially superhabitable surfaces goes up again. Planets, plus moons, plus tidal heating, plus long-lived stars, together increase the odds that somewhere out there, life had better conditions and more time than Earth ever will. That naturally sets up the next question. If some of those worlds and moons are not just better designed, but also older by billions of years, what does that extra time do to their biospheres and to any civilizations that might have formed there? Look at the timeline for a second. Your planet is not old compared to the galaxy that hosts it. Earth is about 4.54 billion years old. The Milky Way is roughly 13.6 billion years old. That gap is huge. There was room for rocky planets to form billions of years before Earth even existed. And a lot of those early planets are still out there right now, orbiting stars that are still burning steadily. When you stand here, in the 21st century, you are not near the start of the galaxy's story. You are somewhere in the middle, looking backward at a long history of worlds that got a head start. Now compare biology's timeline to that. On Earth, life appears pretty early, within the first billion years or so. But complex multicellular life, big animals, complex plants, the things you recognize as nature today, that only really kicks off in the last 600 million years. Dinosaurs, mammals, forests, all of that sits in a tiny fraction of Earth's total age. So ask yourself, what happens on a planet that is 2 or 3 billion years older than Earth, but also stable? You're adding millions of generations on top of everything you know. If Earth has had 600 million years for complex life to diversify, planet with 2 or 3 billion extra years of stable conditions gives evolution maybe 3 to 5 times as long to try things. More mutations, more branches on the tree of life, more chances for complexity to stack up. On Earth, that process keeps getting punched in the face. Mass extinctions reset the board again and again. The end Permian event about 252 million years ago, the end Cretaceous event 66 million years ago, and others each wiped out a huge fraction of existing species. On top of that, you have big swings in climate driven by orbital changes, volcanism, continent breakup and impacts. The biosphere is tough, but it spends a lot of time rebuilding from hits. On a superhabitable planet with better climate stability, fewer giant deserts, smaller temperature swings, and maybe a safer planetary system with fewer huge asteroids on crossing orbits, those reset buttons might get pushed far less often. You still get change, you still get extinctions, but the frequency and severity of complete wipeouts drops. That means more continuous evolution, fewer hard restarts. Complex ecosystems can layer up, diversify, and stabilize over very long times instead of constantly fighting their way back from near zero. Geology adds another layer. Earth's crust and mantle have been recycling material for billions of years through plate tectonics, volcanism, erosion, and subduction. That cycling controls climate, but it also controls chemistry. Minerals form, get weathered, dissolve in oceans, get buried, get reheated, and emerge again in new configurations. Trace metals and nutrients, things like iron, copper, zinc, phosphorus, and many others, get shuffled through different environments. Life then learns to use whatever is available. On a planet that has had more time, those cycles run longer. More crust is processed, more mineral combinations appear, more chemical gradients form at the boundaries between rock, water, and atmosphere. For metabolism, those gradients are opportunities. Every new combination of minerals, gases, and temperatures is a potential niche for a new kind of microbe, a new redox reaction, a new way to harvest energy. Over billions of extra years, that could push biochemistry into regimes Earth has never explored, with more exotic molecules and more efficient pathways. You can think of Earth as a lab that has been running a few experiments for a limited time. An older superhabitable planet is a lab that's been running more experiments for much longer, with better equipment and fewer power outages. The outcome is not guaranteed, but probability starts to push hard in favour of deeper, richer biospheres. Now bring intelligence into it. On Earth, tool-using technological intelligence shows up very late. If you pack everything from the first stone tools to modern computers into a timeline, you're talking only a few million years out of billions, and high technology is just the last few centuries. That's nothing on geological scales. On a planet 2 billion years older, with a biosphere that has been stable for longer, intelligence could appear much earlier in that world's history. It might go through its own version of hunter-gatherers, agriculture, industry, and whatever comes after, with hundreds of millions of years to work with, instead of a few 100,000 or a few million. Even if technological phases are short compared to the planet's age, they can still start far before humanity ever existed. If such a civilization started on a superhabitable world, with more energy, more biomass, and more time, your entire history looks compressed next to theirs. Your industrial revolution, your space age, your digital revolution, all of that might look like a quick, messy trailer at the start of a very long movie. They would have had time to try things you haven't even conceptualized yet, to hit walls you don't see coming, to solve problems you still treat as unsolved, and maybe to run into limits that shut everything down. This is the uncomfortable message hidden in the timeline. There is nothing special about Earth's age that puts it at the front of the line. The physics of star and planet formation say there should be older rocky worlds, some of them likely superhabitable, that had billions of extra years to grow deeper biospheres and, at least in principle, civilizations far ahead of you in time. So now the tension rises. If the galaxy has had more time, better planets, calmer stars, and richer biospheres to work with, why does the sky look so quiet? Are these worlds invisible because we're not looking right, or because their conditions include something else, like better shielding from cosmic radiation, that shapes how life evolves and how easy it is for us to detect it at all? Space is not nice to biology, and your DNA only survives because Earth cheats with shields you mostly never think about. High-energy particles are flying through you all the time, cosmic rays from outside the solar system, plus charged particles and ultraviolet light from the sun. These particles smash into molecules, break chemical bonds, and trigger mutations. On a bare rock with no protection, they don't just chip away at DNA, They also erode the atmosphere itself over long timescales, kicking atoms off into space. Leave a planet naked for a few billion years, and you grind down both the air and the genomes trying to live under it. Earth avoids that fate through a combination of a magnetic field and a reasonably thick atmosphere. Both are products of very specific physics, and both could be better on a slightly more massive, superhabitable world. Start with the magnetic field. Earth's field comes from its dynamo, the motion of molten, electrically conducting iron in the outer core, roughly 2,000 to 3,000 kilometers down, a bit over 1 to 2,000 miles. Convection in that liquid iron, combined with Earth's rotation, generates a magnetic field that stretches tens of thousands of kilometers into space, forming the magnetosphere. Charged particles from the sun, the solar wind, hit that magnetosphere and get deflected, trapped, or guided toward the poles instead of slamming directly into the atmosphere and surface. Now scale this up. On a slightly more massive rocky planet, maybe 1.5 to 2 Earth masses, gravity is stronger, internal pressures are higher, and the core can store more heat. A larger convecting core with more internal heat can keep the dynamo running longer and possibly stronger. That means a magnetic field that lasts more billions of years than Earth's, and maybe extends farther out, creating a bigger bubble around the planet. For life, that buys extra time. On Earth, the dynamo will eventually weaken as the core cools and solidifies more. On a super-Earth, that shutdown might be delayed by billions of years. During that extended window, incoming charged particles see a big magnetic structure and get redirected away from the atmosphere, which reduces atmospheric loss and surface radiation. Then comes the second shield, the atmosphere itself. Even with a magnetic field, some high-energy particles and photons still reach the top of the atmosphere. What happens next depends on how much air there is for them to pass through. Double the surface pressure compared to Earth's 1 bar, go to 1.5 or 2 bar, and you roughly double the mass of air stacked above every square meter of ground. When incoming particles plow into that thicker column, they undergo more collisions, lose energy faster, and create particle showers that get absorbed higher up. By the time the cascade reaches the lower atmosphere, the original deadly energy has been spread out as heat and light. On Earth, you see some of this as auroras near the poles, where charged particles guided by the magnetic field hit upper atmosphere gases and make them glow. On a planet with a stronger field and thicker air, auroras could be more common and spread farther from the poles, but the key point is that most of the damaging radiation gets turned into heat and harmless photons high above ground. The surface becomes a quieter place for DNA to operate. Now look at the stars involved. Massive blue stars, the big O and B types, pump out huge amounts of ultraviolet and X-ray radiation, plus strong stellar winds. They burn through their fuel in only a few million to tens of millions of years, then explode or collapse. No one takes them seriously as homes for life like you. There's simply not enough time for complex biology to develop before the star is gone, and the radiation environment is harsh from the start. Superhabitable candidates live in a very different neighbourhood, around K-dwarf stars, the orange ones. These stars have lower ultraviolet output than the Sun, they burn more slowly, and they tend to be more stable over long periods, especially in middle age. Their flare activity is usually less extreme than that of many M-dwarfs, so combine a calm K-dwarf with a strong magnetic field and a thick atmosphere on a slightly more massive planet. That stack gives you low ultraviolet flux, fewer extreme flares, deflected charged particles, and a deep air column to soak up what gets through. It is the astrophysical equivalent of layered walls and armour, star, magnetosphere, atmosphere, then surface. The consequence for evolution is not subtle. On Earth, radiation events and long-term cosmic ray exposure contribute to mutation, and occasionally to widespread damage. High radiation environments can drive up mutation rates, which sometimes helps evolution explore new options, but often just kills cells or organisms outright. Large bursts from flares or cosmic events can damage whole ecosystems. On a well-shielded, superhabitable world, fewer mutations come from random particle hits, and more come from the internal machinery of cells, from copying errors, chemical reactions, and controlled genetic processes. That does not stop evolution, it steers it. Mutation rates can be tuned by biology, not forced by the environment constantly throwing extra damage at DNA. That shift means lineages are less likely to be wiped out by the sudden bursts of radiation and more likely to be pruned and shaped by competition, adaptation, and internal limits. Diversity can build up steadily, without being reset as often by invisible bullets from space. Over billions of years, that kind of environment can support more continuous, efficient exploration of genetic possibilities than Earth gets. So, if you put it all together, a slightly larger rocky planet with a hotter, longer-lived core, a stronger and longer-lasting dynamo, a thicker atmosphere and a quiet K-dwarf overhead, you get a world where DNA damage from cosmic rays and stellar particles is lower, atmospheric loss is slower, and biological evolution has a cleaner, more stable playground. Earth is protected enough to work, but it is not the maximum shield you can have. And once you've built that kind of safe, high-energy world, another question kicks in. If the star is orange and cooler, and the air is thicker and more humid, what does photosynthesis look like under that light? Do forests and fields even stay green? Or does the truly superhabitable world end up covered in plants and microbes using completely different pigments tuned to an alien spectrum? How sure are you that life has to be green when the star and the air can completely change what colour works best? On Earth, plants are green because chlorophyll absorbs mostly blue and red light and reflects green. The sun's spectrum peaks in the visible range near green, around 500 nanometers, and our atmosphere and oceans filter that light in particular ways. Chlorophyll is a good solution to that setup, but it's not the only possible one. It's just the one evolution locked into here. Around K-dwarf stars, the picture shifts. These stars are cooler than the sun and emit more of their energy in the orange and red part of the spectrum, roughly 500 to 600 nanometers and beyond. Around M-dwarfs, the small red stars, the shift is even stronger toward longer wavelengths. Under those conditions, using the same pigments as Earth plants might not be the most efficient option. Models of alien photosynthesis suggest that life there could lean into darker pigments. Instead of green, you might see deep red, black, dark purple, or even combinations of different colours stacked in layers. The goal is simple: absorb as much of the available light as possible without damaging the molecular machinery. If the incoming light is redder, the energy per photon is lower, so you may want pigments that grab a broader range and waste less. This is about optimizing the photon budget. A K-dwarf star still peaks near the visible range, but a bit shifted compared to the sun. Its main energy output is concentrated around 500 to 600 nanometers, rather than right in the sun's exact sweet spot. Photosynthetic systems tuned to that spectrum could, in principle, be more efficient than chlorophyll on Earth, capturing a higher fraction of incoming light, especially in the orange and red bands. Earth's plants do not absorb all the usable light. They reflect a significant portion of green and near-infrared. That might not be the global optimum, it's just what worked well enough for them in our specific environment. On a superhabitable world where evolution has more time and more energy to work with, photosynthesis could converge on pigment sets that squeeze more efficiency out of each square meter of surface. Then add the atmosphere. Earlier we talked about thicker air being better for shielding and climate stability. That same thick air changes how light reaches the ground. A denser atmosphere with more scattering, more aerosols, and more water vapour will soften direct sunlight. Instead of harsh, sharp beams, you get more diffuse, evenly spread light, something closer to constant, soft daytime. You can think of it like this, not in a poetic way, but as a lighting condition: less blinding direct sun, more broad ambient glow. Under those conditions, plants don't just want to aim at a single angle to catch light. They want to maximise area and coverage. That pushes leaf design toward broader, thinner structures that can capture diffuse photons from multiple directions. Forests can stack those leaves into multiple layers, like natural multi-level solar arrays. Now, throw in the climate. If the planet has low axial tilt, only a few degrees, and orbits a stable K-dwarf, seasonal changes in sunlight and temperature could be mild over wide regions. No hard winters, no long months of darkness, just small variations. That means photosynthesis doesn't need to shut down for months. Every year, many areas could keep running all year, every year for millions of years in a row. On Earth, large regions go through strong seasonal cycles, especially at mid and high latitudes. Trees drop leaves, growth slows, animals hibernate or migrate. The biosphere pulses with a yearly rhythm. On a superhabitable world with low tilt, that pulse could flatten out. Forests would grow continuously. Ocean phytoplankton could stay active year-round over huge areas, especially in broad, shallow seas. The whole global system would have fewer off phases. Over long timescales, that matters. Continuous photosynthesis means more carbon pulled from the atmosphere, more oxygen cycled, more biomass generated, and more steady food chains. Evolution can operate on ecosystems that are always on rather than systems that idle for a third or half the year. You get more interactions, more competition, more specialization, and ultimately more biodiversity. So how does this all look if you were somehow standing there with your Earth-adapted eyes and lungs under one of these orange suns? The star in the sky would be a bit dimmer and more orange than the sun you know, but still bright enough that daytime is clearly day. The light at the surface, filtered through 1.5 to 2 bar of atmosphere, would feel softer and thicker. Shadows might be less sharp. The air would feel dense when you breathe, heavier than at sea level on Earth, but not unmanageable, more like breathing at a slightly pressurized environment. The ground cover could look wrong to you at first glance. Instead of wide stretches of green, you might see dark red or even nearly black vegetation dominating the landscape because those pigments grab almost every photon they can. Leaves could be broad and thin, overlapping in multiple canopy layers, with undergrowth adapted to the dimmer light that filters down. From a distance, forests might look like dense, dark masses with subtle colour shifts, not the familiar bright green. In the oceans and shallow seas, phytoplankton could be tuned to absorb strongly in the red and near-infrared, changing the water's colour and reflectivity seen from orbit. If atmospheric oxygen is higher, you could have intense biological activity in both water and land, constantly feeding and being fed on. Even the grass analogues in open areas could be optimised for continuous growth, with less emphasis on seasonal dying and regrowth. To you, the whole scene would feel like a system that has minimised waste. There are fewer empty patches, fewer bare rocks, fewer long dormant zones. Most surfaces that can host photosynthetic life will be covered by it. And those organisms will be tuned to their environment in a way that leaves very little energy unused. Colour, shape and structure would all reflect that priority. It's not about looking pretty, it's about channeling stellar energy into chemistry with maximum efficiency. From space, a world like this might show very different spectral fingerprints than Earth. Instead of Earth's red edge, the sharp increase in reflectance in the near-infrared due to green plants, you might see a different edge, shifted wavelength, produced by alien pigments. That kind of signal, if we detect it, would be one of the strongest hints that we are actually looking at a biosphere powered by photosynthesis under a different star. Which leads straight into the practical challenge. If life out there is tuning its colours and chemistry to alien suns, and if the best planets and moons are subtle and faint, how do we actually find them from here? And how do we tell which ones are worth pointing our best telescopes at? Right now you live on a planet that can't leave its own neighbourhood, but you're trying to map worlds hundreds or thousands of light years away, using almost no information. So how do you actually do it? The first big tool is the transit method, basically watching stars blink. Missions like Kepler and TESS stare at tens of thousands of stars at once, measuring their brightness over months and years. When a planet crosses in front of its star from our point of view, the star's light dips by a tiny amount, then rises again when the planet moves off the disk. From that tiny dip, you get the planet's radius. A bigger planet blocks more light, so the star dims more. If a star's brightness drops by, say, 1 part in 10,000 on a regular schedule, that tells you a small planet is passing in front. If it drops by more, the planet is larger, simple geometry. From the timing between dips, you get the orbital period, how long the planet takes to go around the star. Plug that into basic gravity, using the star's mass, and you get the orbital distance. That's how Kepler 442b and hundreds of other habitable zone candidates first showed up in the data as repeating tiny shadows. But radius and orbit don't tell you mass, and without mass you don't know if you're looking at a rock, a gas ball, or something in between. That's where the SEN method comes in, radial velocity, feeling the star wobble. Planets don't just orbit stars. Stars and planets both orbit their common centre of mass. When a planet goes around, it tugs on the star, making the star move slightly toward and away from us. High-precision spectrographs on large telescopes can measure that motion by seeing how the star's spectral lines shift very slightly, like a tiny regular change in pitch. The size of that wobble tells you the minimum mass of the planet. A massive planet yanks the star harder, creating a bigger signal. A lighter planet creates a smaller wobble. Combine that mass estimate with the radius from transits, and you can get the planet's average density. Higher density, mostly rock and metal, more like Earth. Lower density, lots of gas or ice, more like Neptune. Radial velocity has been pushed to the point where it can now detect planets less massive than Earth around some nearby stars. Around Barnard's star, for example, instruments have measured wobbles corresponding to sub-Earth mass planets. That's insane precision. You're detecting changes in the star's speed of maybe a meter per second, around 3.5 kilometers per hour, walking pace at distances of light years. So with transits and radial velocity together, you can say, this planet is roughly 1.3 Earth radii, about 2 Earth masses at this distance from a K-dwarf. That's how you build the basic catalogue. But to talk seriously about habitability, you need to know the air, and that is much harder. When a transiting planet has an atmosphere, some of the starlight passes through that thin layer of gas before it reaches you. Different molecules in the atmosphere absorb light at different wavelengths. If you use a powerful telescope and a sensitive spectrograph, you can compare the star's light when the planet is not transiting to the star's light when it is transiting. The tiny differences between those spectra tell you what the atmosphere is made of. This is what the James Webb Space Telescope and other instruments are doing right now. For systems like TRAPPIST-1, where the star is small and the planets are close, the signals are just big enough to work with. For TRAPPIST-1e and its siblings, JWST has already started ruling out certain types of thick hydrogen atmospheres. That is a big deal, because a thick hydrogen blanket would push many of these worlds away from surface habitability. Seeing that some of them don't have that kind of atmosphere keeps them in the still potentially interesting category. In the best case, atmospheric spectra can show water vapour, carbon dioxide, methane, ozone and other gases. Certain combinations, especially if they're out of chemical balance, can be hints of biological activity, though that step is extremely tricky. But you can at least say, this world has air, this one is probably bare, this one has clouds and greenhouse gases, and so on. For now, we can only do this in detail for a small group of planets, but that group is growing. The next leap is direct imaging, actually seeing the planet as a separate point of light, instead of inferring it from shadows and wobbles. The problem is contrast. An Earth-like planet around a Sun-like star is something like 10 billion times fainter than the star in visible light. It's like trying to see a firefly next to a stadium floodlight from thousands of kilometers away. To beat that, you need to block the star's light very precisely. Coronagraphs are instruments built into telescopes that use internal masks to suppress starlight and let the faint glow of planets peek through. Starshades are giant, separate spacecraft that fly in front of the telescope, tens of thousands of kilometers away, physically blocking the starlight before it even enters the optics. Both approaches aim to give you a clean enough view to pick out the planet directly. Missions like the planned Habitable Worlds Observatory are being designed with exactly this in mind. The goal is simple and brutal. Take spectra of Earth-sized planets around nearby stars, including K-dwarfs, and check their atmospheres for water, oxygen, methane, and maybe signs of complex clouds and hazes. Instead of just saying this world has the right radius and distance, you want to be able to say this world has oceans, land, clouds, and an atmosphere like this, using direct data. Until then, you're stuck in a two-step process. First, use transits and radial velocity to build big catalogues, thousands of planets with sizes, orbits, and masses. Then slowly, use atmospheric spectra and early direct imaging to highlight a tiny subset as serious candidates. Right now, the lists of potentially habitable exoplanets contain a few dozen names, depending on how strict you are with the criteria. Some are around M-dwarfs, some around K-dwarfs, a few around Sun-like stars. Some look too hot or too cold, a few sit in the sweet spot. Kepler 442b, Kepler 62f, TRAPPIST-1e, LHS 1140b, and others show up again and again, but none of them are confirmed superhabitable. You're still in the prehistory phase of this field. You know how to count planets, you're getting better at weighing them, and you're just starting to sniff their air. The big decisive step, actually mapping out which ones outperform Earth as homes for life, lies with the next generation of instruments. And that raises the next problem. Even before you can read atmospheres at scale, statistics from Kepler and other surveys already hint that small rocky planets in habitable zones are common. If that's true, then the obvious question is, how common are the ones that fit the superhabitable template? And what does that say about how average Earth really is? Right now, the numbers we've already point in one direction. Earth is probably not rare, but it's also probably not special. Astronomers use a symbol letter Earth for the fraction of stars with roughly Earth-sized planets in the habitable zone. It's not a single magic number. It depends on star type and on what exactly you count as Earth-sized and habitable. But when people dig through Kepler data and follow up observations, one result keeps coming back. Small rocky planets in the right energy range are common, especially around smaller stars. For K-dwarfs and M-dwarfs, rough estimates say that maybe a few tens of % of them host at least one planet that's about Earth-sized to a bit larger, getting roughly the right amount of starlight for liquid water. That means if you pick 10 small stars at random, a few of them probably have a world that checks the basic box. This could be in the habitable zone. We're not talking about 1 in 1,000 here, we're talking about numbers closer to 1 in 3, 1 in 5, depending on the details of the study. Now that's for Earth-like in the broad sense. But superhabitability tweaks the criteria. You're not just asking for any Earth-sized world, you're asking for slightly larger, denser atmospheres. K-dwarf hosts long-term climate stability. So you define another number, call it ETA super. The fraction of stars with planets that match that upgraded recipe. We don't have a precise value yet, but there's a key point. Superhabitable conditions don't demand exotic rare physics. They lean into what already seems easy for the galaxy to produce: small stars with long lifetimes, rocky planets a bit bigger than Earth, and orbits in a certain range. If nature tends to overproduce slightly larger rocky planets, and K-dwarfs are common, there's a good chance ETA super is not tiny. It might even be larger than ETA plus. In other words, better than Earth on paper could be more common than almost exactly Earth. Star demographics back that up. G-type stars like the Sun make up only about 7% of the Milky Way's stars. The bulk of the population is smaller, cooler stars, K-dwarfs and especially M-dwarfs. Those are the real middle and lower classes of stars, where most of the habitable zone real estate sits. You live around a yellow star that looks normal only because that's what you grew up with. On galactic scales, it's not the default. So rewrite the picture. Most stars are not Sun-like. Most long-lived stars are K and M dwarfs, and many of those stars seem to have small rocky planets in or near their habitable zones. When you combine those facts, you don't get Earth as the template. You get Earth as one example, orbiting a minority star type, with only average or even slightly rushed conditions. There's another number that should bother you. One study looking at Earth-sized planets around M-dwarfs estimated that the nearest potentially habitable Earth-sized planet could be only about 9 light-years away. 9 light-years is roughly 85 trillion kilometers, or about 53 trillion miles. That's unimaginably far for you physically. But on galactic scales, it's right next door. Now extend the logic. If planets in habitable zones around M-dwarfs are that common, and K-dwarf systems probably also carry their own rocky planets, what's the distance to the nearest world that is not just maybe habitable, but actually fits the super-habitable wish list better than Earth? There's no precise answer yet, but it's unlikely to be thousands of light-years away. Statistically, it might be tens of light-years, maybe a bit more, but not out at the far edge of the galaxy. Your nearest better Earth could easily be closer than your nearest big spiral galaxy, closer than many of the things you see as bright dots in the sky. The only reason you haven't identified it yet is not that it doesn't exist, it's that you've only just started looking properly. Early exoplanet surveys were heavily biased. They were much better at finding big, hot planets close to their stars, the classic hot Jupiters and warm Neptunes. Those worlds create large brightness dips and strong radial velocity wobbles, so they show up first even with less precise instruments. Only in the last decade or so have you reached the sensitivity needed to see Earth-sized planets in wider orbits, where the signals are weaker and the periods are longer. You're essentially trying to judge the galaxy's entire housing stock after walking through the first few hallways of the building. Most of the subtle, small, interesting apartments are still behind closed doors you haven't opened. So combine everything: star populations, occurrence rates, lifetimes, and the advantages we've talked about for superhabitability. The longer-lived K-dwarfs, thicker atmospheres, slightly higher gravity, better geography, and more stable climates. Put all of that into one statistical picture and ask, if I randomly pick a life-bearing planet somewhere in the Milky Way, what does it probably look like? The answer you get is not a perfect copy of Earth around a sun twin. The answer leans toward older, slightly larger than Earth, orbiting an orange K-dwarf, with more time on the clock and possibly a more powerful biosphere. Earth remains the only confirmed living world you know, but that's because you've only sampled one environment from the inside. The rest of the data you have says your home is more likely mid-tier than top-tier, and that leads to a more personal angle. If the average life-bearing planet out there is not quite like Earth, but a bit upgraded, what would it actually feel like to live on one day-to-day, under higher gravity, thicker air, stronger ecosystems, and a slower, more stable sky? What happens to cities, technology, culture, and ambition when the world itself is super habitable, but the physics of high gravity might keep your rocket ship stuck on the ground? How does everyday life feel when your planet is objectively better for life, but gravity is constantly trying to pin you to the floor? At 1.5 to 2 g, a 70-kilogram human, about 154 pounds, would feel like they weigh 100 to 140 kilos, around 220 to 310 pounds. On Earth, that's powerlifter with a bar on your shoulders territory. On a super-habitable world, that's just your baseline. Evolution there would not build tall, fragile frames. Bodies would skew, shorter, denser, with thick bones, compact joints, and powerful tendons. Running would look different. Top sprint speeds would probably be lower, because every step costs more energy and the impact loads are brutal. But raw strength and static endurance could be extreme. Lifting your own body weight would be routine. Climbing short slopes, carrying loads, or digging would be normal work, not specialized training. If you grew up there, Earth's 1G would feel like walking on the moon dust to astronauts, absurdly light. You'd see gravity written into the architecture too. Tall, needle-like skyscrapers are less practical when structures have to support 1.5 to 2 times more weight. Buildings would trend shorter and broader, with thick support columns and low centers of gravity. Stair steps would be shallower, ramps more common, and floor heights lower, just to keep moving around manageable. The atmosphere changes that picture again. With denser air, lift is easier. Wings don't need to move as fast or be as large to generate enough force to stay up. That opens a whole design space for flying life and technology. Large gliding animals become much more plausible, even in high gravity, because the thick air picks up the slack. You could even get balloon-like organisms using gas bladders or heated air to stay aloft, something that's marginal on Earth but more realistic in dense atmospheres. For a technological civilization, aircraft design swings in their favour. Subsonic planes in thick air are efficient, needing less speed to take off and getting more lift per square metre of wing. Short, wide-body aircraft with big, slow-turning propellers or high-bypass engines would dominate. Helicopter-style vehicles, tilt rotors and gliders would all benefit. They would put more engineering effort into dealing with drag and turbulence, but climbing into the sky would be an everyday routine technology. On the ground, ecosystems would not feel fragile. In a super-productive biosphere, forests are massive, plant growth is fast, soils are deep and rich, and wild species fill every niche. Agriculture in that environment is less about squeezing yield out of marginal land and more about controlling overgrowth. Farmers might be clearing back aggressive native plants that can overrun fields in a single growing season, or dealing with wild herbivores that can strip crops quickly because the background food chain is so strong. Instead of asking, how do we get this poor soil to produce anything, they ask, how do we stop these forests from reclaiming everything? Fences, terraces, and controlled burns, or their alien equivalents, become tools to hold back nature, not coax it into action. Disease pressure from fungi, insects, and microbes would be intense because everything is reproducing quickly, which pushes their medicine and bioengineering hard just to keep farms stable. Daily life would also be tied to a slower sky clock. Around a K-dwarf with fewer catastrophic flares and a long stable main sequence, the external rhythm of the star changes very slowly. If the planet's axial tilt is low and the orbit is nearly circular, seasons are mild or even barely noticeable in many regions. You don't get the severe ice ages driven by big orbital swings that Earth has experienced. That stability seeps into culture. On Earth, big projects that span hundreds of years are rare and risky. Here, long-term climate changes and resource shifts can derail them. On a superhabitable world, it is easier to think in millennia. Agricultural terraces, megastructures, ecological engineering, and even cultural institutions might be planned on 1,000-year timelines. What will this look like in 500 years? Is not a wild question. It's a normal planning horizon. Myths and philosophies would grow under a sky that barely changes over deep time. The star doesn't obviously brighten or shift colour on any human timescale. Major climate disasters are rare. That can create a strong sense of continuity, of being rooted in a world that is stable and generous. At the same time, it can feed complacency. If the environment feels endlessly forgiving, the urgency that drives some of Earth's technological leaps might be weaker. Then you hit the hard wall, spaceflight. Physics refuses to cooperate. To reach orbit from Earth, rockets must reach speeds of about 11.2 kilometers per second, roughly 25,000 miles per hour. Even with that, most of a rocket like Saturn V was just fuel to lift a small payload. On a superhabitable world with 1.5 to 2G surface, gravity is higher and escape speeds climb, maybe by 40 to 50% compared to Earth, depending on mass and radius. That doesn't sound huge, until you run the numbers on chemical rockets. Every bit of extra speed you need demands exponentially more propellant. At some point, chemical rockets become nearly useless as a main launch method. You can still fly aircraft. You might manage small-sounding rockets or suborbital hops, but achieving full orbital velocity and then escape velocity is brutally expensive in fuel and engineering complexity. Rocket stacks would need to be far larger than Saturn V, maybe impractically large, just to push small capsules into orbit. A civilization there could understand orbital mechanics, gravity, and relativity as well as you do. They could build powerful computers, advanced medicine, fine-grained materials science, biotechnology, and dense cities. They might map their solar system with telescopes, detect their own exoplanets, and even discover Earth as a faint, interesting point in their sky. But when they run the launch calculations for chemical rockets, The answer comes back over and over. This is technically possible at insane cost, or practically impossible. To leave, they'd need technologies you don't have working at scale yet. Space elevators with ultra-strong materials, ground-based launch systems that use electromagnetic acceleration, fusion, or other high-energy propulsion directly from the surface, or some kind of staged infrastructure built up over centuries. That's a feedback loop. It's easiest to build that infrastructure if you already have spaceflight, but you can't get spaceflight without the infrastructure, so you end up with a sharp paradox. Their world is a better cradle for life than Earth. More energy, more biomass, more time, more stability. Their bodies are stronger, their biosphere more robust, their climate more forgiving. Their culture might measure its history and future in millions of years, and yet they might remain stuck in their gravity well, physically unable to become a spacefaring species in the way you imagine, at least with anything like your rocket-based path. From our point of view, that sets up a disturbing possibility. This galaxy could be full of advanced civilizations on superhabitable worlds, rich in life, rich in culture, rich in knowledge, but locked down by gravity and comfort, broadcasting little, travelling nowhere, which feeds straight into the bigger problem hanging over all of this. If superhabitable planets are common, and some of them are older and more advanced than you, why is the sky so quiet, and what does that do to the Fermi paradox? If the galaxy has plenty of good planets, and some of them are better than Earth, then the big question doesn't get easier, it gets worse. The Fermi paradox is simple. If life and intelligent civilizations are reasonably common, where is everyone? Why don't you see obvious signs of them? Why doesn't the sky glow with their activity? If you add superhabitable planets into the picture, you're effectively increasing the odds that life starts somewhere. Long-lived K-dwarfs, stable climates, thick atmospheres, optimized geography, deeper biospheres, all of that pushes the probability of life up, not down. Yet your telescopes, your radio arrays, your surveys still see nothing that is obviously artificial. Just stars, gas, dust, and a growing list of silent planets, so the "where is everybody" will question gets sharper. If nature builds better cradles than Earth, and has had billions of extra years to work with, the default expectation should be, there are many biospheres, and quite a few chances for intelligence, but your data still look empty. One possible answer is uncomfortable. Maybe most life is simply too comfortable to leave. On a marginal world like Earth, especially during ice ages, droughts, and climate swings, there is pressure. Food is scarce, conditions change, survival is not guaranteed. Intelligence, tool use, and technology become powerful ways to cope with a harsh, unstable environment. On a superhabitable planet, the baseline is different. Resources are plentiful, climates are mild over huge areas, and ecosystems are dense. In that setting, evolution doesn't need a technological species as badly. Many lineages can thrive as non-technological specialists, filling niche after niche in a rich, stable food web. Intelligence can still arise, but the selective advantage for building tools, industry, and high technology might be weaker. A clever species might get everything it needs from a world that's already generous, without ever being pushed into the high-risk path of industrialization and large-scale energy use. Even when intelligence does show up, gravity and atmosphere can slam the door on space. This is the gravity prison idea. On super-Earths with 1.5 to 2G and escape velocities far above Earth's 11.2 km per second, chemical rockets hit a hard limit. You can do aircraft, balloons, maybe orbital drones launched from tall mountains or special platforms, but getting large payloads off the ground and into space becomes brutal. A civilization might push rocketry as far as it can, build enormous launchers, maybe manage a few tiny probes to orbit, and then hit a cost wall. At that point, going further requires infrastructure and propulsion methods way beyond what you needed on Earth. Space elevators made of ultra-strong materials, gigantic electromagnetic launchers, nuclear or fusion propulsion from the surface. These are huge, risky projects, with long timelines and uncertain returns, in a world where the planet itself already gives you safety, food, and stability. It is very easy to stall out at "we know the physics, but we aren't going to build those machines." So you get civilizations that are advanced in biology, computing and environmental control, but almost completely planet-bound. They might have satellites, high-altitude platforms and amazing atmospheric vehicles, but no large-scale interplanetary presence and no meaningful interstellar capability. From your point of view, they are invisible beyond a narrow radio or optical footprint, if they even bother to transmit anything outwards. Then there's the time factor. Civilizations on worlds 2 or 3 billion years older than Earth are not just slightly ahead of you. They could be ahead by hundreds of millions of years. In that time, their entire technological stack could have changed multiple times, through phases you can barely model. They might have gone through something like your radio age and left it behind quickly, switching to communication modes that are very hard for you to detect, like tightly focused beams, fiber-like planetary networks, or methods that don't leak into space as broad, easy-to-see signals. They might have learned through bitter experience not to broadcast loudly at all. Don't scream into the void is a strategy you can't rule out, especially for civilizations with long memories of risk. Some of them might have collapsed. High energy use, dense populations, and powerful technologies carry failure modes, and older civilizations have had more time to find those modes. Others might have deliberately shrunk their footprint, choosing low-impact, low-output ways of living that leave almost nothing for your telescopes to pick up. A few might have transcended your current idea of civilization completely in ways that simply don't map onto megastructures, radio beacons, or giant engineering projects. Put all of that together, and you get a very unsettling twist. You might be living on a mid-tier planet in a galaxy full of superior worlds. Life could be common, intelligent species could be not especially rare, but the combination of comfort and gravity traps most of them. Superhabitable planets make it easy to live well and hard to leave. That means countless biospheres, possibly many advanced cultures, all locked to their own skies, interacting mostly with their own environment, not with the stars. From your perspective, the universe then looks mostly quiet. No obvious radio chatter, no visible galaxy-spanning engineering, no obvious visitors. But that quiet doesn't guarantee emptiness. It could mean you're surrounded by worlds that do life better than Earth does, packed with ecosystem and maybe civilizations, yet almost all of them are stuck behind physical and cultural walls with little incentive or ability to reach out. So you end up with a grim possibility. The cosmos is crowded, but it stays silent. Not because there is no one else, but because the places that are best for life are also the hardest to escape, and the species that live there don't feel the same desperate push you did to climb into rockets and shout into space. And if that's true, it raises a very sharp question for you specifically. If you ever actually reach one of these worlds, one of the true superhabitable planets, are you going there to fix it? Or are you the fragile outsider stepping into an ecosystem that outclasses your own, trying not to break it or be broken by it? If you ever reach a truly superhabitable world, the big problem is not how to fix it. The problem is how it will rewrite you. On Mars or a dead rock, the plan is simple. You terraform. You try to bend the environment toward Earth norms, more air, more warmth, liquid water, Earth plants, Earth microbes. On a superhabitable planet, that logic flips. You are the fragile one. The local biosphere is older, denser, and adapted to an environment with more energy and more stability than Earth ever had. Your immune system, your lungs, your skin, your gut bacteria, everything about you is tuned to a poorer, thinner, less intense world. The first barrier hits the moment you step out of a controlled habitat. Microbes, every surface, every breath, every drop of water is full of native life built on its own biochemistry, its own proteins, its own toxins. Some of it will ignore you. Some of it may treat you as just another nutrient source. Your immune system knows how to handle Earth's bacteria, viruses, and fungi. It has zero training on a superhabitable world's microscopic lineup. Even if their basic chemistry is similar, details will be different enough that your defenses may misfire or just fail. Allergies, infections, strange inflammatory reactions, all of that becomes the norm until medicine catches up, if it ever does. Then there's the air. A surface pressure of 1.5 to 2 bar compared to Earth's 1 bar means you are breathing more molecules with every lungful. In simple terms, it feels just like sea level after you've been training at the altitude. Easy, dense air that makes each breath feel strong. For short visits, that feels good. But if oxygen levels are also higher, say 25 to 30% instead of Earth's 21, long-term effects get tricky. High oxygen and high pressure together push your body toward more oxidative stress. Fire risk goes up too. Materials that are barely flammable on Earth can burn easily in denser oxygen-rich air. A spark that would do nothing in your living room could start a serious blaze in a forest or a settlement there. You'd have to redesign everything, from fabrics to building materials to electrical systems, around this atmosphere will help burn anything that can burn. Now add gravity. At 1.5 g, your 70 kilogram Earth body feels like 105 kilos, about 230 pounds. At 2 g, it feels like 140 kilos, about 310 pounds. Short term, that's exhausting but survivable. Long term, your spine, joints and heart are not built for that. Bones need to be thicker, muscles stronger, cardiovascular systems more powerful, or you will slowly break down. So if you really want to settle there, not just visit, you need gravity adaptation technology and training. Exoskeletons with powered assistance to help your legs and back. Reinforced suits for heavy labour. Intensive conditioning programs for anyone who plans to stay for years. For children born there, you either let evolution and development do the work, growing bodies that are naturally stockier and stronger, or you start talking about gene tweaks, editing bone growth, muscle density, and even heart structure so they can live a normal life at 1.5 to 2 g. There's a one-way feel to that. A person who grows up fully adapted to high gravity will find Earth's 1 g bizarre. Coming back here after a lifetime, they would feel like being partially weightless. Jumps would be longer, lifting would be easier, bones and muscles would be overbuilt for the load. Everyday movement on Earth might feel like mild moon gravity, not because Earth changed, but because their body is built for a heavier pull. Beyond the physical issues, there is a hard ethical line you can't ignore. Terraforming a dead rock is one thing. Moving into a world that already outruns Earth's biosphere is something else. You're not adding life to a sterile place, you're inserting an entire foreign ecosystem into one that is already complex and stable. Earth life is aggressive, your microbes spread, your plants spread, your insects spread often faster than you can control them, even on your own planet. On a superhabitable world, Earth organisms would be like a shockwave of invasive species arriving from a damaged, stressed biosphere. Some might get wiped out immediately by local competition. Others might find empty niches and explode, pushing native species aside. Either outcome is bad. Either you die, or you destabilize something that was already working better than your homeworld. So you have to ask, do you have the right to drop Earth's biology into that system at all? Even if you try to be careful, quarantine will never be perfect. Microbes hitch rides on skin, equipment, food, air filters. If you set up open Earth-style colonies, the odds of contamination eventually hitting local ecosystems are high. In this scenario, you are not the noble explorer. You are potentially the invasive problem from a degraded world arriving in a place that doesn't need you. And then there's the psychological impact. Humans have always treated Earth as the ultimate reference point, the green standard every other world is compared to. But stand on a superhabitable planet and that story breaks. Fast. You look at forests that are thicker than any you have seen, with multiple layers of canopy and almost no gaps. You see oceans where productivity is higher, with dense blooms of life in shallow seas, stretching for thousands of kilometers, thousands of miles. You breathe air that is richer and heavier. You watch storms that recharge ecosystems instead of ripping them apart. Every instinct that says Earth is the best gets challenged by direct sensory evidence. Looking back at Earth from that perspective is rough. Your home becomes the smaller, harsher, less efficient version. It is still precious, still unique to you, but it is no longer the peak of what a habitable planet can be. It is the place that got you started, the training ground, the feeling you grow up with that the blue planet is the ultimate prize nature can build, gets replaced by a more blunt view. Earth is good enough, but physics and time can do better. That realization cuts both ways. On one side it's humbling, on the other it raises the stakes for what you do next. If superhabitable worlds exist and you are one of the few species that can even think about reaching them, your job is not to show up and pave them over. It's to understand them, to avoid wrecking them, and to decide what role Earth should play in a galaxy where your homeworld is clearly not the top tier. And before you can even make those choices, there's a simpler, more frustrating reality to deal with. Right now you haven't confirmed a single superhabitable planet. You have candidates and models, but your instruments are still too weak to see the details. So the next question is, why? With thousands of exoplanets logged, do we still not have a single official yes, this one beats Earth world on the list? You keep hearing about thousands of exoplanets, so why hasn't anyone pointed at one and said, this is it, this one clearly beats Earth? The blunt answer is, most of what you know about distant planets is just an outline, not detail. For the majority of exoplanets, you have three main numbers: radius from transits, rough mass from radial velocity or statistical estimates, and orbital distance from the period. That's it. That's like judging a city from a dark silhouette on the horizon. You see that it's big or small, tall or flat, but you don't see streets, people, lakes, pollution, or anything that actually matters for living there. When you say this planet is in the habitable zone, you're mostly saying its orbit puts it in the right energy band. You're not saying this is a nice place to stand, you just don't have that level of information yet. The next layer, atmospheres, is where habitability really gets decided, and that's where things get painful. Even with the James Webb Space Telescope, reading Earth-like atmospheres on small planets is right at the edge of what's possible. You're trying to measure a tiny change in starlight as it filters through a very thin ring of gas around a planet, then subtract out all the noise from the star itself, the telescope, the detectors, and the data processing. Stars flicker, they have spots, they flare. Instruments drift, pixels have quirks, backgrounds change. You have limited observing time because every big telescope is oversubscribed. You might only get a handful of transit events to work with, not the dozens you'd really like. That means for most rocky planets, especially those around Sun-like and K-dwarf stars, you simply can't yet say what their atmospheres look like. You don't know surface pressure, greenhouse strength, cloud patterns, or whether they have oceans. You only know that they could be interesting, not that they actually are. On top of that, there's a big bias in where we've pointed our best instruments. JWST and the best ground-based spectrographs are focused heavily on M-dwarf systems like TRAPPIST-1. There's a good reason for that. M-dwarfs are small and faint, so when a planet passes in front of them, the fractional drop in light is larger, and the relative atmospheric signal during transit is stronger. It's easier to see the atmosphere of a small planet against a small star than against a bright big one. But many of the superhabitable scenarios you've been thinking about favour K-dwarfs, not M-dwarfs. K-dwarfs are bigger than typical M-dwarfs, brighter and harder to block out with a small planet. The contrast is worse, the transits are shallower, and the atmospheric signals are weaker. So the very star type that looks best for long-term habitability is also harder to probe with the tools you have right now. You're staring hard at the easiest targets, not necessarily the best ones. Despite all that, the sample size is exploding. As of mid-2025, there are over 7,400 confirmed exoplanets, with thousands more candidates still being checked. Every year adds more systems with small planets in or near their habitable zones. Worlds like HS 1140b, rocky planets in temperate orbits around nearby stars keep joining the list. Most of those worlds are not superhabitable. Some are too hot, some too cold, some clearly gassy. But each new rocky planet in the habitable zone is another test point. Another chance to find a world that fits the slightly bigger, slightly warmer, long-lived star pattern. Statistically, as the catalogue grows, the odds that at least a few true super-habitable candidates are already in there go up. You may already have them tagged with the boring names in a database. You just don't know which ones they are yet. So that's where you are today, stuck between two eras. In the last 30 years, you went from 0 known exoplanets to thousands. You proved that small rocky planets are common and that habitable zone orbits are not rare. You identified multiple could-be worlds that look better on paper than Earth in at least one category. But you're still blind to the details that matter most. Real atmospheric profiles, actual surface conditions, continent layouts, cloud structures, ocean coverage, and biosignatures. You can talk about habitable zones and equilibrium temperatures all you want. You still don't know how many of those planets have deep oceans and thick forests, and how many are bare rock or steam baths. The next generation of telescopes is being designed specifically to break this stalemate. Bigger mirrors in space, better coronagraphs, star shades that block starlight more cleanly, ultra-stable spectrographs, and mission plans that spend serious time staring at a small set of nearby targets. The goal is to move from we know the radius and orbit to we know the atmosphere and maybe even the surface environment. Once that happens, the question shifts from do superhabitable planets exist to something much more direct. Here is one, here is another, here is how they compare to Earth. At that point, you can finally re-rank your own planet with data, not just theory. And when you start that re-ranking seriously, the first testbed will be your own solar system, because if you apply the superhabitability criteria honestly at home, you have to admit Earth might not even be close to the theoretical optimum, just the best of a pretty rough local lineup. How does our own solar system look when you stop treating Earth as perfect and score everything with the superhabitable checklist? If you're honest, Earth still wins here, but more by default than by greatness. Mars is too small and too cold. Its radius is about 0.53 Earth radii, roughly 3,390 kilometers, about 2,100 miles. That small size means weak gravity, thin air, dead core, almost no magnetic field. It probably had thicker air and more water early on, but it couldn't hold them. Long-term plate tectonics stalled, the dynamo faded, and the atmosphere was stripped away. On a superhabitability scorecard, Mars fails at mass, fails at atmosphere, and only passes interesting geology in its early history. Venus is the opposite failure. It's roughly Earth-sized, about 95% of Earth's radius, similar mass, decent gravity, but it sits closer to the Sun, and whatever early oceans it might have had are long gone. The runaway greenhouse turned it into a pressure cooker, with surface temperatures around 460 degrees Celsius, about 860 Fahrenheit, and a surface pressure over 90 bar. That's like standing under 900 meters of water around 3,000 feet. For surface life like you, that's game over. Size, okay. Star, okay. Atmosphere and climate control, complete disaster. Then you look at the icy moons, Europa around Jupiter, Enceladus around Saturn, and others like them. These are some of the most intriguing places in the system for subsurface life. Europa is around 1,560 kilometers in radius, about 970 miles. Enceladus is much smaller, around 250 kilometers radius, about 155 miles. Both are kept active by tidal heating, their interiors flexed by the gravity of their giant planets. Evidence points to global subsurface oceans under tens of kilometers of ice, with probable hydrothermal vents on the seafloor. That checks a lot of boxes for habitability of microbes, liquid water, energy sources, chemistry, and protection from radiation. But for superhabitability, they miss the main point: an easy-to-live-on surface. You cannot walk on Europa's surface and treat it as a normal biosphere. It's a radiation-bathed ice shell over a hidden ocean. Any complex ecosystem is trapped under kilometers of ice, cut off from starlight, operating on a narrow energy budget from tides and rockwater reactions. Fascinating, yes. Superhabitable, no. It's partial credit at best. So inside our own system, Earth still comes out on top for surface life by a huge margin. It has liquid water at the surface, decent gravity, a working magnetic field, active plate tectonics, and a moderate atmosphere. It is habitable, clearly, but put it side by side with the theoretical best case we've been describing, and you see how many knobs are set to good enough, not optimal. Ask what happens if you tune those knobs. Start by scaling Earth up by 20 to 30% in radius. That pushes it to maybe 7,600 to 8,300 kilometers, 4,700 to 5,100 miles. Keep the composition rocky, and the mass goes up to maybe 1.5 to 2 Earth masses. Gravity at the surface climbs to something like 1.3 to 1.5 g, atmosphere retention improves, tectonics can run longer, and the magnetic dynamo gets more time before the core cools off. Then adjust the star, give the sun a bit less ultraviolet output and a longer lifetime by swapping it for a K-dwarf with similar total brightness at the planet's orbit, but a calmer, slower evolution. Instead of a 10 billion year main sequence with you halfway through, you get a 20 to 30 billion year lifetime with far more time ahead. Same total energy delivered, slower changes, fewer nasty flares, less high energy UV pounding the atmosphere. Next, fix the geography. Break Earth's continents into more pieces, more medium-sized land masses scattered around, and extend the continental shelf so more ocean sits in shallow water, tens to a few hundred meters deep rather than thousands of meters. That gives you more coastline, more productive shallow seas, and fewer massive, dry continental interiors. The Sahara, Central Australia, and similar deserts shrink or vanish, replaced by forests, wetlands, and grasslands that can tap into moisture from nearby oceans. Finally, nudge the climate. Raise the global average temperature by 5 to 10 degrees Celsius, 9 to 18 Fahrenheit, in a controlled way, with stable oceans and a robust carbon cycle. Ice caps retreat, permafrost zones shrink, and more of the planet spends more of the year in a temperature range where plants grow fast and water stays liquid. Combine that with a thicker atmosphere and better shielding, and you get a world that's warmer, wetter, and more continuously productive without tipping into Venus-style runaway. That tuned version is much closer to the superhabitable template. Earth, by comparison, starts to look like a beta version, a pale blue dot built to minimum specs. It works, it supports complex life, it got you to spaceflight, but it's not maxed out on any of the key parameters, time, stability, biomass, or shielding. The solar system, when you look at it with this lens, does not look like nature's best work. It looks like a lower-end example in a much bigger cosmic catalogue. So does that mean Earth is irrelevant? No, it means something sharper. Earth is mediocre by theoretical physics criteria, but it's the only place where you have data instead of guesses. All the talk about superhabitability, better continents, thicker air, calmer stars, and deeper biospheres is extrapolation from one known case. This planet, these oceans, these microbes, this evolutionary history. Every model that ranks Kepler 442b or TRAPPIST-1e or any other exoplanet uses Earth as the benchmark. You're assuming that what worked here is a decent guide to what could work better elsewhere. If you find out later that that assumption was wrong in some detail, you will update your entire picture of superhabitable worlds. Maybe high gravity causes unexpected biochemical limits. Maybe extremely high productivity ecosystems are less stable than they look. Maybe K-dwarfs hide long-term flare behavior you haven't seen yet. Whatever the twist is, you will discover it by comparing real data from other worlds to the only test case you understand in depth, Earth. So yes, in a galaxy scale ranking, Earth probably ends up as a mid-tier world, not a gold medal. But it's still the world that produced a species capable of building telescopes, writing models, and asking whether it is mid-tier or not. On the cosmic scoreboard for who is actually doing the measuring right now, your pale blue beta world still sits at rank 1 by default. And that brings you to the final step in this whole argument. If your origin story is probably not the universe's default, if Earth is just good enough in a galaxy full of better options, What does that do to the way you see yourself and your future as a species that just now realizes it probably grew up on a mid-tier world? You've grown up with a very specific background assumption in your head that Earth is the obvious main stage for life in the universe, the baseline that everything else gets compared to. But when you actually stack the physics, the star types, the planet sizes, the climate models, and the exoplanet statistics, that story breaks. The most likely picture is simple and a bit brutal. Earth is not the centre of the habitable universe. It's a good enough planet that happened to get to the space age early as far as you can tell. Run through the checklist. Your star is not the most stable or longest lived type. It's a G-dwarf that will be done in about 10 billion years total, and you're already halfway through that. Your planet is not the optimal size. Models favour something like 1.2 to 1.3 Earth radii and up to around 2 Earth masses. Your continents are not laid out in the most productive pattern. You've got big deserts, deep low productivity oceans, and a history of supercontinents that hammered climate. Your biosphere is powerful, but its total energy capture is limited by geography, climate swings, and repeated mass extinctions. Now compare that to the superhabitable template, slightly bigger rocky worlds, around calm K-dwarf stars, with thicker atmospheres, warmer but stable climates, more shallow seas, more coastline, fewer deserts, stronger magnetic fields, and more time. On paper, that combo beats Earth on almost every long-term habitability metric that matters. Time in the habitable zone, net primary productivity, climate stability, radiation shielding, tectonic lifetime. So your origin story is not we came from the best planet. It's we came from a decent one that was just good enough to get us here. That forces a different kind of humility. You're not from the deepest biosphere the universe can build. You're not from the calmest star or the longest lived ecosystem. You come from a world with ice ages, deserts, impact scars, and a ticking stellar clock. It did the job. It got microbes started. It ran evolution long enough to produce brains, hands, and language. And it stayed in the right temperature range long enough for you to build rockets, radios, and telescopes. But if you ran the same physics billions of times across the Milky Way, most life-bearing planets probably end up with slightly better conditions than Earth. Not worse. That's the humility upgrade, and it's not optional once you've seen the numbers. It means you stop thinking, we are the reference, and start thinking, we are one example, maybe an early one, from a mid-tier world. It also hits your sense of uniqueness. Earth might be emotionally central to you, but physically it's just one point in a very large parameter space. One medium-grade solution to the problem. How do you keep liquid water and complex chemistry running for a while? But that same realization is also a motivation upgrade. If the universe probably contains worlds that do habitability better than Earth, then you suddenly have a clear mission: find them and study them. Not in a vague, maybe there's life out there way, but in a very specific way, build telescopes and instruments that can actually see oceans, continents, clouds, and gases on planets around nearby stars. That means pushing direct imaging hard, building coronagraphs and star shades that can block out the glare of stars and see faint Earth-sized planets next to them. It means flying large space telescopes with stable optics that can stare at a single K-dwarf for weeks and pull out the spectrum of a tiny dot of reflected light next to it. It means building ultra-stable spectrographs that can track subtle wobbles of nearby stars down to tens of centimeters per second to find small, long-period planets you're currently missing. It also means putting serious effort into the software side, into modelling alien atmospheres, alien climates, and alien biosignatures, so that when you finally get spectra from one of these worlds, you can tell the difference between just geology and this sky is being modified by life. You're the first species you know of that can aim its instruments at another star system and ask directly, is this planet's chemistry out of equilibrium in a way that screams biology? In that sense, you're the species that can deliberately look for better Edens. You don't have to wait for one to come to you. You can find them, measure them, and compare them to your own world with the same brutal honesty you applied in this whole conversation. That's not just curiosity, That's how you find out where Earth actually sits in the real cosmic ranking. Then there's the most radical possibility, the one that sits underneath the Fermi paradox and doesn't go away. If superhabitable planets are common, then the universe may not just be biased toward life in general, it may be biased toward life with more of everything, more time, more energy, more stable environments, deeper biospheres, and longer windows for intelligence to appear and mature. In that scenario, there could be civilizations out there that have been stable on their superhabitable worlds for longer than multicellular life has existed on Earth. We're talking time spans of 1 billion years or more, compared to your few 100,000 years as a recognizably technological species. A culture that old, on a world that generous, would not think about history the way you do. Your Stone Age, your Industrial Revolution, your Digital Age would all compress into a tiny flicker on their timeline. Some of them may have collapsed, some may have gone quiet on purpose, some may have gone inward, focusing on simulations, bioengineering, or things you don't have language for yet. But the key point is, physics doesn't stop them from existing. The only thing stopping them is probability, and superhabitable worlds tilt that probability in their favour. And you are here right now in the awkward but interesting moment where this is all turning from speculation into testable science. You live at the dawn of the era when exoplanet astronomy can move from "we know they exist" to "we know what they're like." Over the next few decades, new space telescopes and ground-based giants will start taking spectra of Earth-sized planets around nearby K-dwarfs, measuring their air, checking for water, clouds and key gases. Surveys will expand the catalogue of small temperate worlds from dozens to hundreds. Climate and interior models will get better. Data will start sorting the list into too hot, too cold, bare rock, promising, and eventually this one might actually outclass Earth. At that point, the question is no longer abstract. You'll be able to say, here is a planet 20 light years away, radius 1.3 Earth radii, mass maybe 2 Earth masses, thick atmosphere, lots of water vapour, strong indications of oceans, orbiting a quiet K-dwarf. On every metric we can measure, it looks like a better long-term home for life than Earth. And then you'll have to decide what that means for you. Does Earth stay your emotional home? The place you protect even harder because you now know it's not automatically replaceable in practice, even if better options exist in theory. Do you treat superhabitable planets as sacred study-only targets never to be colonized? Or do you slowly plan for a future where some far descendant of your civilization actually sets foot on one, fully aware that they're the visitors from a mid-tier world stepping into a place built by physics to do life better? Right now, you don't have those answers. What you do have is this, a clear sense that Earth is probably not the gold medal, and that you are living right at the moment when your instruments are just starting to be good enough to find out what actually is. This video is for educational or entertainment purposes only, and information provided. The video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.